Astronomers have spotted a galaxy so far away that it raises troubling questions. For today's video, let's rewind not to the dawn of time, but to 2022. Could black holes be the key to a quantum theory of gravity? A deeper theory of how reality, of how space and time works. Up until 2022, the most distant galaxy we'd ever seen was GNZ1, spotted by the Hubble Space Telescope. It was a landmark discovery. Hubble, with its 2.4-meter mirror and incredible optics, had taken us deep into space, but there was a limit to how far it could see. Then, the James Webb Space Telescope was launched, armed with a massive 6.5-meter mirror and tuned to infrared, the exact kind of stretched ancient light that early galaxies emit. Webb didn't just continue Hubble's work, it crushed its records. In one of JWST's early campaigns, a galaxy named JADES, GSZ 140, was found. It held the record for the most distant confirmed galaxy, with a redshift of 14.32. Redshift in a nutshell is how much the light from a galaxy has been stretched by the expansion of the universe. The higher the redshift, the older the light. Then came MOM Z14 with a redshift of 14.44. It pushed our view even deeper into time. And it wasn't just the redshift that stunned scientists. It was what the galaxy actually looked like. This galaxy is tiny, about 500 light-years wide. For comparison, our Milky Way spans over 100,000 light-years. But MOM Z14 is also incredibly bright. Normally, galaxies this early in the universe should be faint and hard to detect. Not this one. MOM Z14 is bursting with newborn stars, a rapid-fire stellar nursery in the first few chapters of cosmic history. But one feature, or rather the absence of one, made it even stranger. There's no sign of a supermassive black hole. Most of the galaxies we've studied with intense star formation host a supermassive black hole at their center. These black holes are thought to play a key role in galaxy evolution, regulating star birth, shaping structure, and driving growth. But MOM Z14 doesn't. The mysteries don't stop there. When astronomers used JWST's spectrograph to analyze the galaxy's light, they found it rich in nitrogen. Unusually rich. This chemical fingerprint matches what we see in some of the oldest star clusters orbiting the Milky Way, suggesting that MOM Z14 is forming stars in extremely dense environments. That's not what we expected. Galaxies this early in the universe should be chemically simple, mostly hydrogen and helium. But MOM Z14 is telling us that multiple generations of stars had already lived and died before it. That means galaxy evolution may have started much earlier than we thought. It raises a big question. How many more galaxies like MOM Z14 are out there? Before JWST, we thought galaxies this early would be incredibly rare. But now, we've found more than we ever expected. These ancient bright galaxies, sometimes called little red dots, are popping up across JWST's surveys. And astronomers now believe that MOM Z14 may be the record holder as of now. But it might not be for long. And that's where things get really exciting. The more we look, the more we find. And every discovery chips away at our assumptions. If galaxies like MOM Z14 existed in greater numbers, formed stars faster, and were chemically richer than we thought possible, what else are we missing? Does the galaxy challenge our cosmological models? In a word, yes. Our current understanding of galaxy formation says that these kinds of galaxies should be rare, slow-growing, and simple. MOM Z14 is none of those things. It's fast, bright, and chemically complex. It's not that our models are wrong, but they're incomplete. MOM Z14 is a clue that the early universe might have been far more active than we imagined, and this is just the beginning. Later this decade, The Nancy Grace Roman Space Telescope will join JWST in scanning the early universe. Roman will cover much larger areas of sky with incredible detail. Together, these telescopes could uncover hundreds, maybe thousands of galaxies like MOM Z14. Each one a time capsule from an era we're only beginning to understand. But for now, MOM Z14 stands as a milestone, a flicker of light from when the universe was still finding its footing. But the more we probe JWST's findings, the more the universe defies expectations. Some scientists interpreting the data have proposed something bold, that our entire universe might exist inside a black hole. A new research has uncovered an intriguing mystery that the majority of galaxies appear to be rotating in the same direction. The lines formed by the peaks here allow us to identify the direction of the curve of the arms of the galaxies, and consequently, their spin direction. This is significant because in a truly random universe, galaxy rotations should be roughly evenly split between two directions. According to the study's authors, this unexpected finding, which contradicts existing cosmological models, may hint that our universe itself is inside a black hole. To understand this, we need to look at the physics of black holes. When matter collapses under gravity to form a black hole, it creates an event horizon, a boundary beyond which nothing can escape, not even light. Anything that crosses this boundary is forever lost to an outside observer. However, what happens inside the event horizon is still a mystery. This is where black hole cosmology comes in, also known as Schwarzschild cosmology. It suggests that our observable universe might actually be the interior of a black hole within a larger parent universe. Now consider the Big Bang. The Standard Model tells us that the universe began as a singularity, a point of infinite density, just like the center of a black hole. If our universe is actually the interior of a black hole that formed in a larger parent universe, it would mean that the Big Bang was not an explosion in empty space, but rather the moment matter collapsed into a black hole, creating a new universe inside. This has another implication. Each and every black hole in our universe could be the doorway to another baby universe. This could also explain why the fundamental constants of nature appear fine-tuned for life. Because black holes that create stable universes may be more likely to persist and reproduce through this process. The scientists believe that this idea could explain several cosmic mysteries. For example, black holes are known to have immense entropy, which corresponds to the vast amount of information contained in our universe. Another factor that could play a role in this scenario is torsion. In extended theories of general relativity, such as Einstein-Cartan relativity, torsion is a property that accounts for the intrinsic spin of particles and can influence space-time curvature. Some theories suggest that this twisting effect of space-time could generate a repulsive force at extremely high densities, potentially preventing singularities from forming. If true, this could mean that instead of collapsing into an infinitely small point, a black hole could experience a big bounce, where the core rebounds and expands outward, potentially giving rise to a new universe inside. The scientists continued by adding that rapid recoil after such a big bounce could be what has led to our expanding universe, an event we now refer to as the Big Bang. Instead of a singularity exploding from nothing, it could have been a rebirth from the core of a black hole in a parent universe. This theory would drastically change our understanding of cosmic origins, suggesting that the cycle of universes is an ongoing self-replicating process. Another intriguing possibility is that the universe may have a preferred axis. Studies of large-scale cosmic structures suggest a certain alignment in the way galaxies are distributed and move, rather than being entirely random. This so-called cosmic anisotropy challenges the widely accepted cosmological principle, which assumes the universe is isotropic and homogeneous on large scales. If the universe does have a preferred direction, it could point to unknown physics at play, possibly related to the way our universe formed inside a black hole, or how fundamental forces interact on the grandest scales. Moreover, the existence of ancient, massive galaxies so soon after the Big Bang challenges our understanding of cosmic evolution. But while the universe inside a black hole theory is tantalizing, there could also be a more pedestrian explanation for the unexpected observations. Maybe some earlier measurements of our universe are incorrect, especially the speed at which the Milky Way galaxy rotates. In any case, the universe is turning out to be far stranger than we ever imagined, and the uneven galactic rotations will likely prompt astrophysicists to reassess certain aspects of our understanding of the universe. Until then, thank you for watching. Subscribe, share this with someone who loves learning about space and sciences, and come back tomorrow to learn something else.